Okay, welcome back. Let's get started. Sorry about that. Apparently that projector is broken. This projector, the backup, doesn't take 720p. I had a number of solutions and constraints are sort of around 720p, but we're good. We're good. So it might look a little less beautiful than normal, but hopefully it should work. Okay, so today we get to talk about walking robots. How many people went to Sangbei's talk this morning? Awesome. So there's a new mailing list if anybody's interested. Robotics at MIT. If you're not on it, and if you would like to be on it, you can find it in the Athena mailing list and subscribe yourself. But we're starting we've got a seminar series that has local and visiting roboticists that's going to be happening on Tuesdays at 11, and there's food. Okay, so Sangbei gave a talk about his work on a cheetah robot this morning, so it was well timed since we're getting to talk about walking robots for the first time today. Let's just take a second to figure out where we are in the class, right? So we've been talking about acrobats, cart poles, quad rotors, and the like, and I've given you the basic recipe, right? So a basic recipe, computational recipe for dealing with systems of that ilk, right? That are sort of potentially complicated rigid body systems, but so far they've been smooth. They haven't been colliding with the world. They haven't been avoiding obstacles necessarily. But if you have sort of balancing robots that you'd like to control, then doing LQR at a fixed point works very well, right? Doing Lyapunov analysis to figure out where that linear controller works for the nonlinear system works pretty well. Trajectory optimization, I hope you left with the problem set with the impression that actually works pretty well. And you're not supposed to laugh. That was not a joke. And then stabilizing trajectories with time-varying LQR. That works very well. That's a recipe that I think will work well for you in a lot of problems. There's lots and lots of variations for all of those steps. I covered just the basic formulation of trajectory optimization. I put at least call-outs to more of the formulations in the notes. There's lots and lots of variations and extensions. Same thing with the LQR. There's lots of variations. I put a lot of them in the notes too. For instance, if you want to absolutely guarantee that you get to the goal at the end of time, there's a way to formulate the LQR problem that does that. All kinds of variations. Okay, so we've given you a basic recipe that's going to work for a lot of problems, but there's lots of things it can't do. So for instance, we haven't given you tools that are going to always find a trajectory if one exists, right? So let's say I have a quad rotor and I want to fly through a forest, and I start doing trajectory optimization. I say I put a final constraint saying I need to get to this goal in the forest. There's a good chance that the trajectory optimization tools we've given you will try and will fail and just say I can't find a solution. We haven't given you guarantees that algorithm is going to find a solution if it exists. We will give you tools that'll have that guarantee soon, but just understand we haven't given that to you yet, right? And really what we've given you in terms of the trajectory optimization is a local solution. It's something that's going to take an initial condition of interest and maybe some small vicinity, because we're going to stabilize that with LQR, that's going to give you a controller that works from a small set of initial conditions. We haven't yet given you a tool that's going to work from many, many initial conditions. We'll try to give you those tools soon, but we haven't yet. Before we dive into making those tools more sort of address those more complicated problems, I want to play with our basic tools a little bit more on a variety of different systems. Okay, so today is about seeing what it takes to take the stabilization, trajectory optimization, and other tools and understand how they work with something that's just a little bit harder than what we've done so far. We're going to take our balancing robot and turn it into a walking robot. Okay, and the basic details that come in are, for instance, having a hard discontinuous impact with the ground. That's an event. It's a discontinuity in our continuous solutions, and we have to deal with it explicitly. There's another thing that we're going to talk about today, which is the idea that I don't want to necessarily stabilize a point in state space, but potentially a periodic solution of state space. So we're going to talk about limit cycles and limit cycle stability today. Okay? And really today I'm going to talk about the dynamics of walking. And on Thursday we'll talk about how you start bringing those numerical methods to bear on those dynamics. Okay, so let's start talking about walking robots. One of my favorites. Okay, so it turns out, so I've already motivated this by showing you videos of Asimo and videos of passive walkers and told you there's a number of different approaches out there. Some of them rely on the dynamics more heavily. Let me just discuss for a minute here. There's this general feeling that walking is still an unsolved problem in the world, right? So compared to a robotic arm on an assembly room floor, which can do exquisitely impressive behaviors at rates far exceeding a human over and over again, our walking robots fall down a lot. They use 20 times more energy than humans when we walk, and they're generally considered not where they should be in the world. Things have come a long way in the last just few years, but there's something still fundamental about what we can't do with walking robots, right? All right, so what makes walking so hard, right? I'll give you a short list here. Right. First of all, walking robots are just inherently complex, right? You end up with robots that have many degrees of freedom, many links, right? So you just end up with complexity from that. I honestly don't think that's not a big problem. That's an okay problem, but that's a practical problem that if you end up building a walking robot, you got wires running everywhere, you got just hardware issues, right? Compared to a quad rotor, those things just work pretty easily, right? There is a problem that goes along with that, which is that you do have to carry your actuators. So to some extent, there's a fundamental interchange between having actuators that are powerful enough to do everything you need to do versus the size of the actuator you have to carry, right? So Songbei actually addressed that beautifully today. He talked about his actuator selection strategy for Cheetah and designed some custom actuators that gave instantaneous torques that were sufficient for his running experiments, but it required a custom actuator. But what it means is, oftentimes we're dealing with input saturations or power limits sort of beyond what you might have to do if you were a robotic arm that had a tether to the wall, right? There's been a few dramatic exceptions to that rule. So for instance, Boston Dynamics has been building robots based on hydraulic power with a gasoline engine attached. And gasoline is basically unlimited power. So if you're willing to go there, then you can get around some of the fundamental limitations. But the electric humanoids have traditionally suffered from not being able to move their legs as fast as you'd like to, right? So the big difference is if I get pushed and I have hydraulic power, then I basically can put my leg back as fast as I need to catch myself. That makes stabilization relatively easy. If I'm a humanoid robot relying on a geared electric motor and batteries, and I get pushed, then it's somehow I have to be smarter about getting my leg back because I can't just move it back arbitrarily fast. Okay, so actuator limits are absolutely real. Okay, I can't believe this is my third one, not my first one. Systems are underactuated, right? Right. So fundamentally, where a robotic arm is bolted to a table, a walking robot is not bolted to the table. It has degrees of freedom. It by definition has more degrees of freedom than it has actuators. Right. It's not because I don't have enough funding. It's because fundamentally, if I'm not bolted to the ground, I have extra degrees of freedom. If I put an actuator between my foot and the ground, I'm not going to walk very far, right? Okay, so these things, I think, we've already developed some tools to deal with. Okay, there's other things that we haven't dealt with yet, right? So I think the complication that comes with impacting the ground. That's a new sort of complexity that we're going to deal with today. The other one I said is that often the goal is periodic behavior. So we're going to start talking about limit cycle stability. So these two are sort of the goals for today. So start addressing those. And then there's some other really, in practice, sort of very important practical problems, right? So it's, these robots are just fundamentally difficult to model. Unlike some of their, like a wheeled robot or certainly a factory room robot, they depend on their interaction with the ground, for instance. And so you either need to perceive the ground at with high quality perception, estimate the friction properties of the ground you're about to walk on, right? It's fundamentally, there's just a lot of uncertainty out there, and it's hard to have good models, right? Even if your robot internally, sure, you can get a good model, but it's hard to know, if I step on that rock, is it going to teeter and fall, or is it going to stay, right? It's fundamentally hard to know the dynamics of your robot. And your robot, a walking robot, depends so heavily on its interactions with the environment that makes it very hard. And going along with that, not having the model, there's no global reference frame for a walking robot. So there's a premium on state estimation. And I'd say as a community, we're still getting our head around the state estimation problem for walking. But there's been good local work on that. Okay, so we're not going to get to those today, but we'll at least give we'll talk about them a bit towards later in the class. All right, so roughly speaking, I showed you videos of Asimo. And Asimo is amazing. I don't mean this to sound as a critique of Asimo, but I just want to, there's a strategy out there that, you could sort of call Asimo's strategy. I think Asimo is actually supremely good walking robot. It's extremely robust to rough terrain, far beyond what people give it credit for. Okay, but I think they made a point initially that there is a strategy out there, which is that you can worry about some of those ideas less, especially the underactuation and the impacts, if you restrict your dynamics a little bit in an important way. So if you keep one foot flat on the ground, here's my little Asimo, okay. Second leg. All right, that's pretty good. My kid would be proud. Okay, and if I look at the ground reaction forces of this foot on the ground, which you can measure locally with local load cells and the like. There's a few heuristics which are very important to the problem, which Asimo and a lot of the electric humanoids in the world make use of, right? There's a basic strategy, which is to look at your ground reaction forces and summarize these ground reaction forces as some sort of net ground reaction force. You can compute what's called the center of pressure. of those ground reaction forces, which is just sort of an average. This center of pressure is also known as the ZMP. You've heard of that, the zero moment point. There's subtle differences, but for the purposes here, they're the same. And the basic observation is if I can keep my center of pressure inside my foot, not at the edge, then my foot will not rotate. Okay? Okay, and you can generalize that to if you have multiple feet on the ground, then what matters if I look down from the top, if I have sort of foot 1 and foot 2. Then what matters is the convex hull of my support and having the COP be somewhere in the middle of that, okay? But if I can put a constraint somehow on the dynamics of all my links here, to make sure that the center of pressure stays inside the support polygon. It's called the support polygon. Then I know that my foot will not rotate. Okay? If I know that my foot's going to stay flat on the ground, then in some sense I've taken away a degree of freedom from the robot. Right? I can pretend for a little while that my foot is bolted to the ground, and I can start acting like I'm a fully actuated robot again, right? Right? Subject to the constraint that whatever motions I choose to execute, I don't cause my center of pressure to hit the edge of the support polygon. As soon as I do that, my degree of freedom comes back, and I'm in danger of being underactuated again, right? So if you're willing to sort of do fully actuated things subject to that constraint, then you can do a lot of impressive things, right? So a lot of the initial work on humanoids would, for instance, follow almost arbitrary trajectories. You would motion capture someone doing an exotic dance, put it through a sort of a filter, which makes sure that none of the accelerations during this motion are going to move my center of pressure to the edge of the support polygon. Once you've sort of done that filter and you map it onto the robot, then the robot can go off and do its dance, right? And basically execute, and they do, right? There's plenty of videos out there. There's lots of great dancing robots, right? So, or you can do it with potentially motion planning, although that's potentially hard for the big robots, but there's been great work on that. Okay. But I think one of the big observations is if my center of pressure is squarely inside my foot, then I can start acting like a fully actuated robot again. It turns out there's this idea of the center of pressure and the ZMP has turned out to be more important than that, and we'll talk more about this later, but roughly there's a lot of great planning ideas. It seems that the calibration is not great down here, but if I look like I'm not writing well, well, I guess it's true, but it's not all my fault. Which plan sort of the center of mass and center of pressure trajectories of the robot first. Then fill in the details. Because it turns out that this can be an extremely efficient plan planning sort of algorithm and capture a lot of the dynamics of the robot. So for instance, when you look at our Atlas, when Scott showed you videos of Atlas walking around, you might have noticed that its feet were often flat on the ground too. We actually, just to plan really fast, will plan center of mass and center of pressure trajectories. But then when we stabilize plans, or that's just for walking on the flat, when we stabilize plans, we do this quadratic programming controller that Scott told you about, which is capable of stabilizing those plans even if the foot is rotating and things like this. So it's sort of got the underactuated approach built in, right? But the super fast planning exploits these low-dimensional approximations of the center of mass and center of pressure. Okay, so that's one of the reasons that Atlas also walks often with flat feet. But you'll see increasingly videos of Atlas jumping off blocks and doing other things that are more dynamic that don't have that same constraint. Okay, so this idea of regulating the center of pressure in ZMP is extremely powerful, but it's also a little bit limiting, right? It's fundamentally very conservative to walk with your feet flat on the ground. And in fact, this idea that the specific case where the center of mass and center of pressure planning is very powerful is when your center of mass actually stays exactly horizontal. It doesn't change elevation over the course of a stride. And that is fundamentally why humanoid robots walk around like this, right? Everybody asks, why are the knees bent, right? It's actually not because the knees, it's not so much to keep the knees bent, it's because they want to keep the center of mass at a constant height, okay? We do too, it's a great idea, because everything gets simpler when you keep your center of mass at a constant height. Then first of all, if your center of mass is actually at a constant height, then you have no impact event. Your foot, if you did have an impact event, your center of mass would have to change height, but you'd have no energy sort of in your impact, so you can basically ignore the impacts that we're going to talk about today if you keep your center of mass at a constant height. Second of all, it turns out the dynamics of your center of mass relative to your center of pressure are linear, so you can actually do linear planning with constraints. So it's a type of, but it's a linear systems kind of idea to do planning with the center of mass, and that's why it's super fast. Okay, so that's the reason why humanoids walk like that. And then if you think about the goal of keeping your center of mass at a constant height, now you want to take your longest possible extension, your longest possible step, with your legs mostly straight. Okay, that means if your center of mass is at a constant height and you have to be able to step like this, then there's going to be this sort of awkward fact that when you're at the normal stance, your knees are pretty bent, and everybody for the rest of time is going to ask you, why do you walk around with your knees bent, right? Life goes on. But that's you know, so that's why the robots are walking with their knees bent, is because they're trying to keep their center of mass flat. Okay, so it's sort of a fundamentally, and even just when your feet are flat on the ground, what you miss out on is a lot of the energetics of walking. You don't push off with your toes. You don't strike with your heels. You tend to take shorter strides. Okay, all these things sort of hurt your conservatism and your how natural your gait is. So it's a conservative but robust approach, right? So Asimo walks around everywhere. He walks around office environments. He's ringing the bell on the stock exchange. He's conducting symphony orchestras. He's doing stage shows. I mean, that's a level of sophistication that most of our robots have not reached, right? So it really, really works well. But it uses something like 20 times as much energy as a human when it walks, because it's walking around with its knees bent all the time. It's not pushing off with its toes. It's not striking with its heels. And its energetics are sort of not human-like. Okay? Right? So we showed you this other approach of these passive dynamic walkers. And what I want to start talking about today is some of the simple models that are going to capture the dynamics of the robot of walking that maybe Asimo's missing out on, or that maybe we still need to work into our humanoids control. It turns out some of the simple pendulum kind of things you've already learned are going to help you understand walking. I think most of the story is sort of in walking pretty quickly. Does that make sense? Anybody have any questions about? Yeah.
Can you write a little larger?
Sure. This is the whole 1020p, not 720p. I'll try to write larger. Questions? Yeah.
What does that word after powerful planning say?
Ideas. It doesn't look much better down here, honestly, but ideas. Which, yeah. Plan, center of mass plus center of pressure trajectories first, then fill in the details. Yes?
So what's the motivation in putting so much effort into walking robots when wheeled robots already perform pretty well?
There's always someone who asks that question. Right? So why not just use wheels, right? So in fact, there's a lot of answers I can give, right? But one of the things I will say right off the bat is that there's this DARPA challenge that happened. And everybody said the wheeled robots are going to rule the day and the walking robots are going to embarrass themselves. And 5 out of the 8 teams were bipeds. And other teams had more legs too. So I think, even though I said walking's still hard, I think we've gotten to the point where walking works well enough that we have to stop. We don't have to apologize anymore for doing walking robots. But the arguments typically for walking are that the world is built. There's actually a lot of the world that's not accessible by wheels. Quadrotors get to a lot of them. But a lot of them where intermittent terrain is very hard for wheels on. Something like these stairs here, I think a tracked robot could cruise up, but a ladder is hard, right? And there's an argument that if we've engineered the environment for human-like forms, then maybe a human shape is the right thing to build. I don't really subscribe to. If you've got a problem where wheeled robots work well, put some wheels on. I think that's totally cool. I think that walking robots force a lot of the right issues that are important for a lot of different robotics. If you care about manipulation or something, which is hard to do with wheels, then it turns out a lot of the same algorithms apply. So for me, it's the right challenge to see something in biology that works so well, and we just take it for granted. Walking's not hard for us, and it's somehow so hard still for our control ideas. That means that's the problem that we should be looking at for me. Yeah.
When you generate, when you're talking about generating a model, and that's hard. When you're just doing it for the actual robot, do you actually derive that from physics, or do you go out and just experiment and empirically try to figure out what the control is?
No. So for the robot's dynamics, we start with the Lagrangian. We fit parameters using physics-based models. For the world, we'll use data. Yeah. But so there's this new thing that's happening, which is soft robotics, and I don't know yet whether Lagrangian mechanics is the right starting point for that. But I think for rigid body robots with pins and joints and torque type actuators, we have a really good start with the Lagrangian equations, and parameter estimation works very well in that class.
What if you pick something up and it changes?
Yeah, but even that we can accommodate pretty nicely. Yeah.
My question was, how easy is it to completely center of mass to change whenever you try to do something?
It's true. It turns out it works pretty well. Right, so a lot of times you put a load cell in the hand to estimate some carrying load. You don't have to have a perfect model of the object you're manipulating, for instance. If you just know its contribution to your hand, you can factor that into the contribution of the whole mass. And in practice, these guys do walk around. In practice, a lot of them use just the center of the hip as a surrogate for the center of mass, right? And that's still it's sort of a robust enough idea that estimate doesn't have to be perfect. Cool, yeah.
What makes it fully actuated when we bolt one foot?
So let's just count. So if I put if my foot was bolted to the ground here and I have a motor at every joint, right? I know this is not drawing bigger yet, but it's on my old drawing, so I'm grandfathered in. Right, so I literally have an actuator on every joint, right? Except for the ones that would connect me to the world. If I'm to assume that this is fixed to the world, then by just counting up, then I can say that I have the same number of actuators as I have. The problem is if my foot goes up to a pin joint, right? Because I'm rotating around here, then I don't have an actuator here. There's no torque here. No torque actuator here. Yeah?
Thank you.
And if I'm flying through the air, then I've got 6 degrees of freedom in my body that has no actuator unless I've got a jetpack on, right? Okay, cool. So although humanoids and human-like walking is extremely hard to get your head around, There are some very beautiful, simple models that are going to capture a lot of the physics of walking that we're going to be able to get our head around almost completely in the next few minutes, 40 minutes. Okay? So the first one is called the rimless wheel. Okay, so here's my cartoon. Okay, those are all the same length. I've got a angle here. Well, let's count them out. So what are the degrees of freedom of this robot? In general, I've got the x, y position of the body plus the orientation of the robot. Okay, but if I add some assumptions, if I assume that that this foot doesn't slip in the world, and I ignore the fact that if I just say the dynamics are invariant to x, y location, if I don't care about that, then I can actually, with some assumptions, write the dynamics down completely in terms of theta and just give up on tracking where the robot is in the world. Okay, so I'm going to assume that there's a pin joint here. Okay, and just to have all the parameters, I'm going to say that the legs are length L. Okay, I've got, let me make it a little bigger here. Green stuff, okay. Thank you. So I'm going to have length L. I'm going to call this angle here between the spokes 2 alpha. You'll see why I call it 2 alpha. And then the angle in the world is theta. There's a mass m. And I'm going to put it on a ramp because wheels don't do as interesting things on the ground. Okay. And I'll say it's on a ramp angle gamma. Okay. And we're going to make some basic assumptions. So, well, note first of all that I've defined it the way I've drawn it here. Theta equals 0 is upright. Okay, compared to what we had before we had theta is down. Okay, let me list some modeling assumptions. It's going to make everything clean for us, okay? So first of all, there's a pin joint at the toe. So that means we're assuming no slip, that there's enough friction that once my foot's planted, it's not going to slide. Whenever the wheel rolls around and this next foot comes into the ground, I'm going to assume that that collision is inelastic. And impulsive. So it happens instantaneously. And furthermore, that there's an instantaneous transfer of support. Right? So my model is this thing's going to spin around that point until the next foot comes around and hits the ground. At that point, there's going to be some collision event. This point's going to suddenly have a pin joint. This one's going to release, and that all happens all at the same instant. Suddenly, I'm rotating around the new point. Okay? And the consequence of this inelastic assumption is that this rules out there's no bouncing. Right? I can never have an aerial phase. So no. Never going to leave the ground. There's always exactly 1 foot on the ground, and there's also no double support. Okay, so here's a rimless wheel, roughly inspired by that model. Okay, so I guess on the flat it's not so interesting, but we have a big ramp upstairs that gives it more interesting dynamics. Okay, we assume that there's a point mass at the hip, and that the mass of the leg is relatively zero compared to the mass of the hip. Okay, and then when you build them, you have to build two, otherwise it falls over sideways. Right? Okay, but that's what you should have in your head when you're thinking about the rimless wheel. Okay, it turns out it's a beautiful, beautiful system. Right? So I had to reboot for the projector. Okay, so as we're going to see, if you give this guy a little push on the ramp, he's going to start rolling, and he's going to end up doing something sort of beautiful. He's going to fall into a perfect, periodic, stable oscillation. Okay, and we're going to understand all the details of that. Okay, so let's start thinking about the dynamics of this pendulum. Okay, so problem with writing bigger is I run out of space. But okay, so this is worth writing down if you haven't. Good. Okay, so I hope that was already said. All right, so let's think about, it's basically a simple pendulum, right? So if I draw my phase diagram of my simple, it's not only a simple pendulum, it's a undamped simple pendulum, right? So you know about what the phase diagram of this guy looks like, right? It's my eyeball again. Okay. But there's a few important things going on in this picture now. So there's a moment where collision happens, right? This whole angle is 2 alpha. The bisection of that angle is alpha. Okay. If you think about the angle at which this collision happens, this is gamma, so this angle has got to be gamma. This is alpha, so this angle has to be gamma plus alpha. Yeah? Did I say that right? This one here is alpha. This one here is gamma. Just by okay. So there's a defining moment in these phase diagrams here where theta is gamma plus alpha. There's another one on the other side where it's gamma minus alpha. Okay, it's actually going to be true. Okay, so this is here's a hypothetical orbit of the rimless wheel. Okay, let's say I started some initial condition here. The phase diagram has me going this way. I'm going to move happily along here, until something dramatic happens. I smash into my foot smashes into the ground. By my assumptions, I'm going to have an instantaneous event where I'm going to reset my coordinates. So theta becomes when theta was gamma plus alpha, it's now going to instantly reset to my new coordinate system around here. So theta becomes gamma minus alpha. So I've moved over to here. But also I'm going to lose a little bit of energy because of the collision. We're going to figure out what that energy is. So I'm going to end up sort of doing something like this. Okay? And then I'll start going again as the dynamics of a simple pendulum. And I'll smash into this again. I'll come back here. Okay? And we're going to understand sort of that dynamics of what happens in that repetitive motion. Okay? But it's exactly the phase diagram of the simple pendulum, just zoomed in a little bit with some collisions going on. Let's make sure we understand the dynamics of that inelastic collision. Okay, so the inelastic collision, what it means to be inelastic is that, intuitively what's happening here is that means that all of my energy that's going into the ground is lost, right? Okay, so think about the dynamics of my pendulum here. Okay, so at the moment of impact, immediately prior to impact, my velocity was moving. Let's say I was moving on this previous. I was working with this. This was my pin joint, so I was rotating this way, which means my total momentum of my system, my velocity of my center of mass, had to be tangent to that, right? My center of mass was moving on that arc. So instantaneously, I had a velocity, and what matters really is my momentum. And I'm going to cartoon it as v minus, which is going to be just before collision. Okay. Immediately after the collision, my foot's going to be rotating around this point. And I have to, because I'm a rigid body attached to the pin joint here, it has to be that my velocity is now tangent to this. Right? But I don't gain any energy. The only thing I've done is I've lost energy by smashing into the ground. So this vector here has to be, this basically all energy that was going into the ground was lost. This is mv plus. And this thing in the middle, which is my losses, if that makes sense. I have momentum right before, my momentum right after. I know it's in this line, okay? But its magnitude is exactly what it has to be, which is I haven't gained any energy. I've kept exactly the energy that it's consistent with this new constraint, right? Well, now that I'm operating around this pin joint. Okay, so it's the projection of this vector onto this new constraint. Okay? Another way to see that is by writing down the angular momentum. So immediately before the collision, well, actually, let's do immediately after the collision. Immediately after the collision, angular momentum about collision point Okay, immediately after, I just have the length of my leg cross MV plus here. Which, since that's a right angle here, is just L times ML theta dot plus. Okay, the velocity here is just L times theta dot. That's something you might not have seen, but that works out to be true. Okay, and then if I look at beforehand, my angular momentum around this, it's still L cross MV. Okay, but now the length there, you know, the cross product is now L ML theta dot minus, but with this cos 2 alpha in the middle. Remember, this is 2 alpha. Okay, so if I set the angular momentum before and after the collision to be the same, then what that tells me is that theta dot after the collision is exactly theta dot before the collision times cosine 2 alpha. Yeah?
So I just want to ask the direction of velocity energy. Is that, just to make sure I understand that? That way,
That's a cartoon. I don't really like drawing an arrow for energy, but what's true is that it makes sense to talk about the vector of the momentum here afterwards, and all I'm saying is that vector afterwards is got to be the projection of this onto that new surface. So this saying calling that a vector of energy lost is sort of that's just me trying to be colorful. Yeah, I don't want to call energy a vector. Okay, so that's cool. So the rule here, in all this complexity of my collision, didn't work out to be so bad. It just turns out that theta dot afterwards went down by cosine 2 alpha. Okay? Let's just make sure that makes sense. I mean, a couple sanity checks. So what happens if alpha goes to 0? I've got no losses, right? So I haven't modeled rolling friction, but if I'm a wheel, then I've got no losses in this model, right? And I guess if 2 alpha goes to pi over 2, then I'm a block going down and I lose all my energy, right? All right, so that sort of makes sense, right? Okay, so it turns out that this simple, do you understand the dynamics, right? So if I can simulate with the pendulum dynamics, I'm going to do, literally in the simulations, we do event detection. We simulate the differential equation. We watch till it passes over some threshold, and then we actually go back and check to find, as close to numerical tolerance, the exact time when it crosses that threshold. We apply this map, and then we start simulating again. Okay? So that's how the dynamics go. And then let's see what it does. Let me just run it for a couple different initial conditions and see the variety of things that can happen. All right, so here's my standard initial velocity. It turns out it started off fast, and it slows down into what looks like, and we're going to see, is a stable periodic motion. Okay? That's awesome. That's beautiful. So what's happening? How can that possibly be stable? There's two things going on here with the energy of the system. It's gaining some energy by going down the ramp. It's losing some energy every time it hits hits its foot on the ground. And somehow, for that to be stable, those things are exactly balancing. Okay? Yeah?
That seems to be a critical point, that it's a function of the angle of the slope.
We're going to see exactly how it changes. But I can tell you that if I change the slope, it's gonna change the walking speed, but it's gonna be pretty robust to that. Until you do something like make it 0 or make it 90, and those are, yeah. But in the middle, it's pretty, the walking speed will change. The number, well, you'll see exactly, yeah. But it's pretty robust. It's not a magic number. All right, so let's try a couple different numbers. And these are not magic numbers, but they're selected just so you can see the range of different behaviors. Here's a faster speed that actually still slows down, okay? Even from a lot of initial velocity, it still slows down to that same limit cycle, okay? Turns out if you start slower, you can just end up standing still, right? What happens if you go backwards up the ramp? If I give it some initial velocity backwards, I can just go backwards and stand still, okay? But let's say something almost the same, okay? I'm gonna start backwards. I can go back over and end up rolling forwards in the stable cycle. Okay, so there's sort of two stable behaviors in the system. I showed you both of them. One is standing still. The other one is rolling forever, okay, in a stable cycle. We're going to see all of those in that simple phase diagram, okay? You're going to be able to completely understand it. This is the only walking system you'll ever completely understand, but it's satisfying. Okay, so just to be clear, what's happening there? So there's a couple different things that can happen. One of them is this thing can go and end up in a stable limit cycle up here, where the amount it's going down is exactly balanced by the amount it goes up by the fact that this is adjusted by gamma, right? So it's moved to the right of this by gamma, and you get a perfect stable limit cycle up here. There's another thing that can happen, which is you can end up going, let me see if I get my colors right here. Okay, so you can end up going like this, dink, and then you come over here, dink, and you slowly run out of energy, and you end up sitting still like that. It's actually pretty subtle, though. To call that a fixed point is tough, because it's actually only a stable fixed point in the sense of undergoing infinitely frequent collisions. So that's called the Zeno phenomenon. It's one of the nasty points of hybrid systems. Okay, so that thing sitting still is in the simulation. That when you see multiple zero crossings, you see that little warning that comes up every once in a while. That's it saying, you know, I'm finding every time I simulate a step, I see lots of zero crossings. Okay, and then it can also go backwards. So if it can also be over on this side here. So simulates like this. And then comes back, simulates like this. And if it goes like this, it gets caught in this minima here. Okay, but if it ends up right, there's a point where it can end up right here, jump over and end up going back into this forward limit cycle. Okay? All right, so the goal is to analyze the stability of this cycle. That's our goal. Somehow everybody had to turn a page at the same time, huh? All right, so the first question here is, what our notion of stability is going to be? Okay, so is this solution trajectory that I'm talking about of the pendulum, where it's rolling forward forever? Okay, is this is the solution trajectory? Sorry for the shorthand. Solution trajectory. Let's call it x0 of t. Is it asymptotically stable? Right, so for a trajectory, what I would like to have is that does x of t go to x naught of t? Or the distance between x of t x naught of t go to 0. Locally, say. What do you think? Yes or no? It's actually not asymptotically stable because of a really subtle but important point, okay? I'm going to flip back just to make that point, and then we'll go right back here. There are two neighboring trajectories that I can pick, which will never converge. Imagine I start an initial condition here and an initial condition here, okay? They will both go around the same cycle for all time, but the distance between them will never go to 0. Okay? That's a fundamental defining feature of orbital limit cycle stability as opposed to trajectory stability. Okay? I say a convergent phase, right? The phase in the cycle need not converge. Right? So if I have some, in general, some oscillator moving around in phase space, right? These two may never converge. Okay, so somehow our tools that we've already got for Lyapunov analysis and the like are going to have to either address that or get thrown to the wayside. Okay, so this notion of a periodic solution that's stable or could be unstable is the notion of a limit cycle. Okay, so it's different than trajectory stability. It's the notion of systems that converge but not necessarily in phase. Okay, a limit cycle is a locally stable or potentially unstable periodic solution. Okay. Now, I say it, so I think there's nothing wrong with calling a marginally stable cycle periodic solution a limit cycle, but people typically don't do it. I mean, you don't typically say that every orbit of the undamped pendulum is a limit cycle. It's just, but so typically we reserve the limit cycle to something that's sort of a unique trajectory which is locally stable or unstable. Okay, so but what do we mean by stability here? Okay. What we'd like is that solutions x of t are going to converge to somehow to the manifold of possible of that periodic orbit, right? So what I'll write it like this. I want these two things are going to go to 0. Okay, but t might not equal tau. And in fact, what I want is the minimum over tau of this to go to 0. Does that make sense? If I'm here and I want to see how far I am from the trajectory, then I get to look over x star. I get to look at all time and find the closest one. And this will be my distance, right? And if I'm here, then I've got a smaller distance. And I'm saying the distance between this new trajectory and the whole manifold of solutions has to go to 0, but that's importantly different than the trajectory stability. Yeah?
So what if we're like have a pendulum that's rotating one direction versus the other direction? How does this tell? Because like this is directions.
Those are different places in state space. You can only go one direction in state space. So I think it's still consistent. Yeah, that's still in orbit. Okay, so the rimless wheel is not stable in the sense of trajectories, but it is stable in the sense of a limit cycle. Okay? I see some people look really happy. Some people are not. Some people are tired. They're working on the problem set until 2:39 or 2:29. Some people don't look so happy. So ask questions if you have. Okay. All right. So let's pull the simple example first. Okay. So we can do an example of limit cycle stability without impacts first. And I'm going to pull out that van der Pol oscillator, which I talked about very, very quickly before. We were talking about regions of attraction. Okay, so van der Pol oscillator is just some second order system. Okay, so it's a second order system. You should think of this almost as a linear spring damper system. The only problem is that it's got some nonlinear damping, if you will. Right? In particular, when Q squared is less than 1, or Q is less than 1, then this is actually putting energy into the system. And when Q is greater than 1, it's taking energy out of the system. Okay, so it's, my normal mass spring damper would just sort of decay away to 0 if I just add positive damping. This one's actually putting energy in at the low velocity, so it's actually going to spin out. Okay, until it gets to the point where it starts taking energy out, and it's going to find a balance and end up in a stable limit cycle that looks something like this. Oh heck, I can't draw it as well as I can show it. Okay, so at here, if I'm just plotting the vector field of Q versus Q dot, then I get trajectories that go out like this, and they hit this stable, sort of beautifully shaped limit cycle. Okay, and then similarly on the outside, it's actually energy is decaying, and it'll converge back to here. So this is a known sort of limit cycle oscillator system, which in time looks like some oscillation. Okay, but in phase converges to this nice limit cycle. Okay, so how are we going to think about stability of this? I'd like to reason about the stability of the van der Pol oscillator. Okay, we're going to do it by introducing the idea of a Poincare map. Okay, so So I'm going to define a surface of section. Let me just draw this cycle a little better once over here. Let's define a surface here. That's only wide to try to make it visible, but we're going to call this thing a surface of section. Okay, it's for an n-dimensional vector space. It's an n-1 dimensional surface. Okay, and it has to be a useful surface, to be well defined as a surface of section, it has to have the property that trajectories flow through the section. And always return. So every trajectory that goes through will find its way back to go through again. Okay? So if I do that, then you can imagine charting this system in its higher dimensional space by charting its progression through the surface of section. Okay? And what you get is now a new, you have my original x dot equals f of x, but on the surface of section, I get a new discrete dynamical system, which tells me where I land on this n minus 1 dimensional Poincare section as some function of where I was in the previous crossing, on the nth crossing. So it's a discrete time system, which maps from the nth crossing to the n plus 1th crossing. Yeah? This one happens to be now, if I take my two-dimensional van der Pol oscillator and I draw my surface of section, okay, and I end up with a n minus 1 dimensional, so I get a one-dimensional map. And the same way we could draw everything visually with the one-dimensional maps in continuous time, we can do everything visually with the one-dimensional maps in discrete time. So let's draw the one-dimensional map of the van der Pol oscillator. If I plot xp n versus xp n plus 1, okay, there's a defining line, which is the line of slope 1. On which, if I'm at this line, right, when I come in at xp, at a certain xp, and if xp n plus 1 equals xp, then that's a fixed point. Yeah? The same way, if I'm above the line here, I'm going to speed up. If I'm below the line, I'm going to slow down. Okay, it turns out that the van der Pol oscillator has a return map that looks something like this. If you look at its progression through, at low velocities, it's speeding up, okay? And at high velocities, it's slowing down. And there's a great theory of how you can sort of there's a whole nice, in the Strogatz book, for instance, this is an iterated map. And there's great pictures you can draw on this. I can chart the progress of this if I start at some xp, and I look at where I end up in the map, and then I project that to the next xp, and I get this sort of these staircase diagrams that help me simulate the system forward using the graphical analysis, and you see you end up at the fixed point. Similarly, this one, if I start at some xp like this, my next xp is going to be here. In order to bring it from this axis to this axis, I project it to the line of slope 1. Then I bring it down here, here, here. I get these staircase diagrams. Okay, so this one, this discrete map, is asymptotically stable. And like any discrete time system, you can look at the eigenvalues and determine its stability locally, right? What's interesting is that assuming the derivatives exist, assuming you're away from any strangeness in the surface of section, if you're locally a valid surface of section, then local stability on the Poincare map is actually necessary and sufficient to give stability of the limit cycle in the n-dimensional space. Okay? That's a big time idea that says I can look on the Poincare map, I can do nonlinear fixed point analysis on the map, and I can bring my results back to say something about limit cycle stability on the original system. Okay? All right. So it turns out that I was going to walk through the math, but I've talked too slowly now. So I can draw the rimless wheels return map. Okay? If you can solve it pretty easily. You can just look at the energy conservation to figure out what my dynamics are from before the switching surface to the next switching surface. I've already given you the dynamics of the impulse going back, and I can write down that the rimless wheel Poincare map is that gives me theta n plus 1 is cosine 2 alpha. I mean, you don't have to write this down, it's in your notes, but it's something that looks like theta squared plus some other terms here. Okay, so I'll take a map from right after the nth collision to right after the n plus 1th collision. Okay, and if I draw this for one particular choice of slope, then what I get is the angular velocity at the nth collision versus the angular velocity at the n plus 1th collision. I get this beautiful map that looks like this. Okay? Where this thing asymptotes to cosine 2 alpha, something with slope cosine 2 alpha. Okay, so it's definitely less than 1 in the asymptote. Initially, it's above the line, and you get a stable fixed point right here. I guess I can really cheat. Look at that. Okay, here's the whole answer. If you plot it even for the unstable fixed points, you can see that there's another map down here, okay, with a fixed point at standing with 0, 0. And even more so, if you do your staircase diagram, okay, up here, I start up here, I go bink, 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 bink. I end up always at the rolling fixed point if I started too fast. Down here, I staircase up to this, okay. When I'm in here, I can staircase around and get stuck in this standing fixed point. There's this little strip right here where if I started at this velocity, I bounce up here and I bounce all the way over into this rolling fixed point. I go here. Okay, and then this is the rolling uphill case now, right? Over here. It happens that there's strips, right? This is now the basin of attraction of the rolling fixed point is this mesh, right? And if I started here, then I come out, I end up in this region, and I'll ultimately end up in the rolling fixed point. If I start over here, I end up there, and there's strips that go out, and they expand as you go backwards, with the expansion rate exactly equivalent to that cosine 2 alpha of dissipation. So this whole thing is a contraction over time, every one of those steps gets a little closer, and I can find myself, I can completely understand what happens. I end up in one of those two fixed points with the basin of attraction completely characterized. It's the only walking system you'll completely understand, okay? But the beautiful thing is, the story there of keeping energy, getting energy from gravity, losing energy from dissipation, holds for much more complicated systems. And you can get there sort of in stages. So the next step is you take the extra joints, the extra legs, and put a pin joint in the middle. And this is called the compass gate walker. You put some mass on the legs, otherwise it doesn't make sense. You don't have any dynamics of your legs. Okay, but you put this guy on a slope. You do the same analysis. I can't anymore solve for it in closed form, but we can do all the numerical analysis and show that this thing falls into a same stable limit cycle behavior. The problem is this guy also falls down a lot. The rimless wheel can't fall down, right? It's globally stable to either one of those two fixed points. This one has another one which is hanging upside down, which is really annoying. Okay, and in practice, it's really hard to build these. We've tried, and they mostly just fall down. And especially to get the masses right, to make it all the mass collected at the hip and a massless leg, we've shattered so many robot legs because we tried to make the leg really light, and then we take a step and shatter the leg, and it's everywhere. You can even do it with more legs. Okay, so if you put a knee joint at the hip, now this one has an extra collision which happens at the kneecap. Okay, and that's essential for the dynamics. Not only do you not want your leg to be swinging around just like a quadruple pendulum, but this one actually has a collision event. Energy is lost at the knee strike. Energy is lost at the collision, and then it keeps going. But this also has a stable limit cycle behavior, which you can exactly understand with the Poincare map analysis. Okay, in these we can numerically evaluate the Poincare map. We can linearize around the Poincare map to ascertain the local stability, but we don't have closed form expressions for the Poincare map. So you can't even do like Lyapunov analysis on the Poincare map directly, because you don't have a closed form expression for that to throw into sums of squares or something. We'll get around that, but these are great problems. Okay, so simple models of walking actually tell a lot of the story, and we're going to be able to throw all of our computational tools into this with just throwing in a little extra care to deal with limit cycles and impacts. I'll see you on Thursday.